I'm going to go through the answers to these Unit 12 practice tests. So the first questions here are some matching about alphas and betas and gammas and positrons. So it requires 1 meter of concrete to stop that. That's the gamma ray. Okay, gamma rays are very, very difficult to stop. Carries a negative charge. Okay, negative charge, that's a beta particle, which is an electron. Is a helium nucleus. We all know that's an alpha particle, helium 4/2. Okay, for this one here, we need the little numbers. The top number you can see is going to be 0. Okay, because the 137, 137. We got to look up cesium. Cesium is number 55. Barium is number 56. Those are the atomic numbers. So this must be a -1 here. So 56 minus 1 gives you 55. So that's a beta particle. Answer B. Has the greatest mass of the 4. Okay, well, actually alpha particles are like, several, almost 8,000 times heavier, so alpha particle. And it's used to kill bacteria. Now, this is some of the trivia, about uses of radioactivity. There was a handout we didn't give out. It's online. There's a video that goes over it, and it's on your 8-station review. And you can look on the station and see all those statements are true, so those are good stuff. So it does, yes, they use that to kill bacteria on packaged fruit, and it will keep the fruit a little bit, better, longer, and that's gamma rays. Okay, next question here. In a cloud chamber that we built, alpha particles leave longer tracks than beta. No, they're shorter. That's not true. Gamma rays, you can't see gamma rays. Okay, the dry ice is used to cool the chamber so radioactive particles can be emitted. No, they're going to be emitted no matter what. The tracks are seen when the alcohol condenses on the radioactive particles. Oh, boy. Okay, well, that's the best answer. That's not really correct, though, however. Okay, because what happens, the little, say this is the radioactive material, things are shooting out of there, and that ionizes the air, and then the fog kind of condenses on those little positive ions. So those little positive ions are not necessarily radioactive. So that's the best answer, because the other ones are certainly not true, but that's not really true either. Okay, Henri Becquerel, okay, he did not discover X-rays, that was Roentgen. He did not coin the term radioactivity, that was Curie. He did discover radioactivity while he was looking for something else. He was looking for another source of X-rays. And making new elements, no, he never made new elements. Okay, so 8 is C, discovering radioactivity. Okay, number 9, which of the following is not an example of radioactivity? Okay, being exposed to UV rays, no, that is not radioactivity. That would, however, be called radiation. Light, different forms of light, things that radiate out, that's radiation, but you would not call that radioactivity. Americium-241 in smoke detectors, certainly that is radioactivity. Gamma rays to check for weak points, yes, and using technetium as a radio tracer, those are all radioactivity. So the only good answer is answer A. Okay, for number 10, what's the half-life of the decay of the graph above? So we say, okay, we're starting up here. I think our numbers are a little bit off. They're not too bad. So this guy here starts up here above 160. How long does it take to get down to half? Well, that looks like it's about 180. So when does it get to 90? Right about here. So that looks like it's about a time of 4 hours. I would say that that is answer B. And I will double check my answers here. And yeah, that's right. Okay, we could also start someplace easier, like, looks like there's no really good easy places on here. Here's like at 120, so how long does it take to get down to 60? So again, that's 4 hours. So just pick any spot and see how long it takes to get down to half that much amount. Okay, what percent of the original sample remains after 12 hours? Well, if you're talking about percentage, okay, then that means we are starting with 100%. That's just implied. And we say, okay, 4 hours, 12 hours, we're talking about 3 half-lives. So it's going to go down to 50%, it's going to go down to 25%, it's going to go down to 12.5%. So that's the answer, okay, for here. So number 11 is B, 12.5%. Okay, the decay of thorium involves an alpha decay and then 2 beta decays. So what's the result? Well, we could write this out as 3 separate little equations here. Okay, thorium, I'm looking on my periodic table, that's number 90. I need that number. Okay, or I can write it out as one big equation. Okay, if this gives off an alpha particle, and then it's going to give off a beta particle, and another beta particle, okay, I can treat that all as one big equation. So the 232, 400, so it's going to be 228 on top. And the bottom minus 2, 2 minus 1, that's actually 0, so it's going to end up being thorium, but thorium that weighs 228. Thorium 228, that's answer A. And that's how I can do that problem. Okay, 13, I'm in the wrong place. Oops. Okay, 13. The isotope bismuth decays from 60 grams to 7.5 grams in 1 hour. What's its half-life? Well, is it a whole number of half-lives? Let's try that the easy way. So if I had 60 grams, it would go down to 30 grams in one half-life. That would go down to 15 grams in another half-life. That would go down to 7.5 grams in another half-life. So it looks like 3 half-lives is 1 hour. So 1 half-life must be 20 minutes. So 1 hour divided by 3, 20 minutes. Answer D. In the nuclear equation, A and Z are what? Okay, so we are saying, let's fill in this middle guy here. So what do we have left over? So on the top would be 234, because 234 plus 4 is 238. And the bottom would be 90. We know that is thorium. We just did that a moment ago. So the two numbers, okay, Z is the bottom number, so we're looking for 90 and 234. 90 and 234 looks like answer A. Okay, number 15. Iodine 131 has a half-life of 8 days. What percent would remain after 100 days? Okay, again, it says what percent, so it means start at 100%. And 8 days and 24 days, so I can see I'm going to have 3 half-lives, 1, 2, 3. It's going to go down to 50, going to go down to 25, going to go down to 12.5%. Okay, so that is answer A. Okay, number 16 involves some mathematics, so I kind of did it here. So it says the measured mass of neutral lithium-6 is this number here. So what is the mass defect? So if I have lithium that weighs 6, that means I'm going to have 3 protons, okay, because that's every lithium. Since it's 6, that means I have 3 neutrons when I subtract those 2. And if it's neutral, that means I have 3 electrons. So if I know the mass of an electron, a proton, and a neutron, I'm going to take 3 of them, 3 of them, and 3 of them, okay, get their masses, okay, add it together. So that's the mass I would expect, but this is the real mass, okay, so I'm going to go ahead and subtract that right here. And the number I have left over, that's going to be called my mass defect. That's the mass that disappears. And what does it do? It turns into energy by E equals mc squared. Okay, but we're just looking for that mass defect, so 0.034364. That looks like answer C right there. Okay, 17. 1 mole of water has a mass of 18 grams or 0.0180 kilograms. Calculate the the energy in 1 mole of water if all of its mass were changed to energy. So we're saying for this E equals mc squared, but joules, if I'm working with joules, that means that it must be kilograms and meters per second. So my mass here is going to be 0.0180 kilograms, and the speed of light we know is 3 times 10 to the 8th meters per second, and that's squared. So when we dig it down and do all of that, then we find out that the number we're going to get is 1.6 times 10 to the 15 joules. So it's just a plug and chug problem for that. Number 18, the rate constant is 0.231 minutes to the minus 1. What's the half-life? Well, we know if you take the natural log of 2 and divide it by the rate constant, then you're going to get the half-life. So we could take 0.693, which is ln of 2, divide by 0.231, and then we get the answer of about 3 minutes, answer B. So that's just, again, just a math problem. Be sure you know this formula. That's a really useful little formula. 19. The half-life of bismuth is 5 days. What's the rate constant? So it's exactly the same thing we just did, only going the other way around. So we say, well, what have I got? I'm going to say the natural log of 2, 0.693, this case, if I divide it by the half-life, then I get the rate constant, and so it's going to be 0.693 divided by 5, 0.693 divided by 5, and it's going to be days on the bottom, so days to the minus 1. That comes to be 0.14 days to the minus 1. Okay, number 20, a sample of neptunium with a half-life of 4.4 days is allowed to decay for 7.1 days. What's the percent of the original sample that remains? And again, because it says percent, that means we're starting with 100%. Okay, well, we can see what's going on. It's, allowed for 7.1 days. That's not even a whole number of half-lives, so we can't do our simple problem here. Although we can get a quick guess here. Okay, 50%, 25%. Okay, that would be 8-point-something days, 8.8 days. So we know our answer is going to be somewhere between 25 and 50. Okay, so I can knock off A, I can knock off D. Okay, I can't knock off B and C. I have to calculate. Now, I have to go back now and actually use my equation. Okay, and the equation for this is the first order rate law. And first order rate law, as we all know, is, I'm going to change colors. I'm going to move down here so we have more room. Okay, so that's the natural log of the mass at time t minus the natural log of the mass at time 0, okay, equals negative kt. Okay, now, we know the half-life is 4.4 days, so we can do what we did before up here and say, okay, if I did natural log of 2 divided by 4.40 days, okay, that's going to give me my value of k. And for that, I get a value of 0.1575, and that's days to the minus 1. Okay, so 0.1, that's my value for k. And what do I know? I know my time is 7.1 days. And I know that that is 0.1575 days to the minus 1. So those units cancel. And my initial value, we're going to call that just 100%. Okay, so I have natural log of 100, okay, minus natural log of x, and we're just solving for x. And when we're all done, we get 32.7. Okay, we get this answer, answer C. So it's a math problem. You got to do the natural log of 100. We got to multiply those two numbers. And then what we're going to do is to put that together, take E of both sides, and we come up with 32.7. Okay, for the free responses, what's the half-life of barium? We're going to read that off the graph. So if we start at 8, okay, how long does it take to get down to 4? That looks like 10 days. Okay, no work shown. It's just, look at the graph. After how many years will 0.5... I'm sorry, that's 10 years, not 10 days. Okay, I would have lost the point. How many years will only 0.5 grams remain? We're starting with 8 grams. So I'm going to find out, can I just do this simply? 8 grams down to 4 grams, down to 2 grams, down to 1 gram, down to 0.5 grams. Yeah, so this is a whole number of half-lives. So if I have 4 half-lives and they're 10 years per half-life, then this is going to be 40 years. Okay, there are more sophisticated ways to do this, but that's the right answer. Okay, draw on the graph the decay if it was only 5 years. Okay, so I'll change colors. So I would, after 5 years, I would go from 8 to 4, and then I would go from 4 to 2 in 10 years, and then 15 I'd go down to 1, and then after 20 years I'd go down to 0.5. So I would get a graph that looks something like this. Okay, and that's what I have for 5 years. Okay, now cesium undergoes beta decay and releases gamma rays. Write the nuclear equation for this reaction. So I got cesium 137, 55, okay, undergoes beta decay, so that means on this side I put a beta particle, and gamma, okay, that doesn't make any difference in any of my numbers. And so what I finish this off, so the top is 0, 0, so this is 137 on the top, and the bottom 55 equals x minus 1, so it's going to be 56, and 56, I think we saw that before, that's barium. So that's the equation, a little bit messy, but that's it. Okay, the half-life of this stuff here is 30 years. How many grams of a 160-gram sample will be left after 100 years? Okay, well, you can see what's happening is we do not have a whole number of half-lives, so we're going to have to go back and use our integrated rate law. So the natural log of the mass at time t minus the natural log of the mass at time 0, the initial mass, equals negative kt. Okay, again, t we know is 100 years. Okay, k, we're going to go ahead and calculate that again, and I'll change colors here. So that's the natural log of 2 divided by 30 years. Okay, so that's 0.693 divided by 30 years, and that comes out to be 0.0231 years to the minus 1. So these two are going to get multiplied together with a negative sign in there. Okay, let me clean that up there. And so what do we have? We have 160 grams. So our initial sample is 160 grams, so the natural log of 160 grams. Okay, and this is the natural log of x. So again, we're just going to get all our numbers. We are going to take the e of both sides, and we end up with this x, the mass at time t is 15.9 grams. So I'm leaving the math for you to do, okay, but that's how we set it up. Okay, write the nuclear equation for this reaction. Okay, sodium 22/11 decays to form neon 22/10. So we just have to fill in what's again. So the top is going to have to be 0. This bottom one must be a 1 because 10 plus 1 is 11. So that is a positron. Okay, if the half-life of this stuff is 2.6 years, after how many years will 87.5% of the original amount decay? That is a tricky wording, and it's designed to say, well, a lot of people will try to use that 87.5, and that's not what you want to do. We'll say after how many years will that much decay? Well, then how much is left? Subtract from 100, you get 12.5%. So what we're really saying is if we started with 100%, okay, how long would that take us to get down to 12.5%? And we've already seen that a couple times. Okay, that's going to take us 3 half-lives. So if 3 half-lives at 2.6 years per half-life, okay, then we're going to get an answer of 7.8 years. Okay, now you can also go back and just use, the full equation and everything, but this works for whole numbers of half-lives. Okay, 24. Americium-241 that we use in smoke detectors undergoes alpha decay. So Am-241/95. Okay, alpha decay means put an alpha particle over here on the right. 4/2. So the top number is going to be 237. The bottom number will be 93. And if I look at my periodic table, number 93 is neptunium, Np, and that's my equation. Okay, a 2-gram sample decays to 0.2 grams in 1430 years. What's the half-life? Well, first off, is this easy? Can I do it with just numbers? So 2 goes down to 1, 1 goes down to 0.5, 0.5 to 0.25, 0.25 to 0.125. Okay, I'm in trouble. So my answer is going to be somewhere right here. Okay, so it does all this in 1430 years. How much is each one? We can kind of see it's 3 in a fraction half-life. So if that was 1500, it would be 500. So it's somewhere around 500 years is our half-life. But we're going to have to go back and use our actual equation. And we've seen this a couple times. Okay, so we're going to say natural log of the mass at time t minus the natural log of the mass at time 0 equals negative k times t. Well, what do we know? The total time is 1430 years. Okay, we want to find the half-life. So if we could find k, okay, then we could change that into the half-life. So what do we know? We know the mass at time t is 0.2. So the natural log of 0.2 minus the natural log of 2, which is 0.693. So this is a number, this is a number. Okay, this is a number. We're going to solve for k. Okay, so if you go through and mush, 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 k comes out to be 0.00161, okay, years to the minus 1. And if we want to get the half-life, so we know the half-life is equal to the natural log of 2, 0.693, divided by 0.00161 years to the minus 1. Again, that comes out to be 430 years. And again, I'm leaving all the little math for you to do, but that's the setup. And that's the practice test.